All right, everyone. So we're going to be taking a look at bond energies today. So this is going to help you out. You can take a look at the other lesson as well, but I just wanted to go over this with you quickly so we have a better understanding. So when we look at bond energies in this unit, we have been taking a look at how we're able to calculate the amount of heat that is released by any reaction by using the quantity of energy that is associated with that chemical bond when we look at both of the reactants versus the products. When we look at a covalent bond that is between two atoms, in order to break them, we have to have enough energy in order to do so. So the energy required to break the chemical bond when a substance is found in the gas phase, once again, we can only use that for the covalent bonds. It is known as bond dissociation energy. So bond dissociation values, which is known as D, are seen as positive values, and that is the energy that must be absorbed by the reactants in order to break a bond. So for example, if we have our OH bond, which is found in water, we can also find it in ethanol and propanolic acid. If we were to look at that example, it has an average bond energy of 467 kilojoules per mole. And therefore, if we're looking at, in order to break that 1 mole of the OH bond, we have to have 467 kilojoules of energy in order to break that bond into 1 mole of oxygen and then 1 mole of hydrogen. So that is how much energy is needed in order to break it. We can also say that we have 467 kilojoules of energy that is released when 1 mole of OH bonds are formed. And I've also attached a table of the average bond energies of the several different covalent bonds that is shown on our D12 shell, so you can reference that in the future as it's not necessary to memorize them. So when we look at multiple bonds and bond energy, when we look at the multiple bonds, they have larger bond energies than single bonds. So in this situation here, the bond, so this is a single bond, we have a double and then a triple bond. As you can see, the larger the bond, the more energy is needed. So the bond energies increase as the bond increases. As the number of bonds increase, the number of electrons in that bond also increases, and therefore we have an increase in the electrostatic forces. And then on top of that, that also shortens the bond length and it has an increase in bond enthalpy. So you can see here, these are the bond lengths of some of the most common bonds. So we're bonding different carbon or oxygen, nitrogen, depending, and it can have a single, double, or triple bond type. And as you can see, the larger the bond type, the larger the bond energy is, but also on top of that, the bond length decreases. So if we were to compare the bond types here, the increase in bond type and increase in bond energy, but the bond length decreases. So that's important to remember here. So when we're looking at enthalpy and bond energies, the bond energies can be used to calculate the enthalpy change for any reaction, and we've seen this symbol before. So during a reaction, we look at the bonds and the reactants that must be broken. In order to do that and have to break them, we have to have energy added, and this is known as an endothermic process, and therefore the bond energies must be positive. But if we are making new products and not breaking them up, then that means energy is released, and that is an exothermic, which is a negative reaction that occurs. So these two are very important to remember. I would star them if I were you, and so you just have a better understanding. So therefore, if we know the type of bond that must be broken and formed, then we can use the following equation and the table of bond energies to calculate our change in enthalpy. So we have our change, and then we have the sum of energy to break the bonds, which is our energy required. And then that is subtracted by the sum of energy to form new bonds, which is our energy released. Okay, so the sum in order to break the old bonds is positive value, and that means energy is required, and the sum to form new bonds is negative values, and that is energy released. And then remember, N in this situation is the number of moles of the bond in a particular molecule, and that is obtained from the balanced equation. So here it is again. We just took a look at. Remember this symbol right here that we can see from the situation, the equation, that is sigma, and that is known as the sum of. So that sigma is known as the sum of. The N is the amount in moles of a particular bond type. And then D, as we know, is the bond energy per mole of bond. So D is always positive. We talked about that earlier. And it is obtained from the table given to us. And then you can see that negative symbol between the reactants and the product. That negative sign changes all the bond energies in the products to negative values, okay, because it is a formation of bond releasing energy. So you do not have to put the change in bond energies, put the value from that table, okay? And then some important facts is bond energies can only be used to calculate the enthalpy change of a reaction, and only if all the reactants and products are in the gas phase. We can't do it in any other phase. So an example here, so we have using bond energies in table 1, calculate the enthalpy change for the reaction in which hydrogen gas is combined with fluorine gas. So both of them are gases, which is perfect, to produce 2 moles of hydrogen fluoride. So this reaction is represented by the balanced equation. And then first step is to draw the Lewis structures of the reactants and products. So we have 2 hydrogens, and then we have 2 fluorines, but we know how many it has on its outer shell. And it is formed to create 2 of each, okay? So based off of this, we can also write out what is required, which is the change in H, and then what is given, we have H2, and based off of our information, we know that the N of our hydrogen bond is 1 mole. For F2, the bond of our fluorine is 1 mole. And then for HF, which is the product, that is NH minus F, that is 2 moles, okay? So we know that. And then if we look at our table, our D values, which we were talking about before, and that comes from our chart, D of H bond is for 32 kilojoules. I'm just pulling up my chart again because I do not have it on me. And then the D of our fluorine bonds. Where's fluorine? It is 154. And then HF is 565 kilojoules per mole. And this is all kilojoules per mole, by the way. Alrighty, so combining our information, we can write it all out. So the change in H is N, which is our H bond, and then our D, H bond plus N of our fluorine, D of our fluorine, minus our HF, and then DHF. So therefore, it is 1 mole times DHF DH plus 1 mole times DFF minus 2 moles times our DHF. Now combining all this information, we have 1 mole, and that is going to be times 432 kilojoules over mole plus 1 mole times 154 kilojoules per mole, and then minus 2 moles times 565 kilojoules per mole. So now, if we put this onto a calculator, we will get an answer of change is negative 544 kilojoules. Why is it not mole? Because the moles cross each other out. So therefore, it releases 544 kilojoules of energy. Therefore, the enthalpy change is negative 544 kilojoules. So therefore, we'll write this out. It releases 544 kilojoules of energy. Therefore, the enthalpy change is negative 544 kilojoules. Okay? So that is how we are able to solve for it. I want you to try out example 3 here. We just skipped an example 2. So please do take a look at this. You can organize it in whatever way possible. Okay, so the first step is to balance the equation. Okay, that's going to be on the next page. And then step 2 is determine the bonding of each substance by drawing the structured formulas. Okay, so what is the bond? And then step 3 is determine the number of moles of reactants and products. Okay, so that is the number of moles of bonds broken or formed and the molecular bond energy for each. And then step 4 is calculate the enthalpy change. So step 1 with the balanced equation, that is on the next slide. I'll show you that in a minute. So pause now. Try to balance it out. Try to figure it out. All right, this is the equation. So that is balanced out. So balanced. Step 2 is determine bonding. So we have HC, which is a triple bond of CH, because it's C2H2. Then for our O2, this is a double bond. For our H2O, single bond, and then for our CO2, it's a double bond. Now, step 3, number of moles. So, you can do this by drawing out a table if you like. Drawing out a table if you like. So saying substance, number of moles, amount of bonds, and then bond energy, and then you can have your reactants, and then products. So we first have C2H2 and O2, CO2, H2O. So we know the CH is 2 moles. The C triple bond is 1 mole. Okay, because when we look back, this is a bond and this is a bond. Then for O2, that's a double bond, but it's 1 mole. Okay, on top of that, we have C double bond with the O, that's 2 moles because it's 2 different elements. And then HO, that is 2 moles. Okay, now the amount of bonds, we have 2 moles and then 1 mole. For the O2, that's a 5/2 mole. Okay, and that came from our equation. Then we have 4 moles for CO2, and then we have 2 moles. Okay, and that's how we make sure that it is properly balanced. And then now taking a look at the bond energy. Oops. We have 413 kilojoules per mole. We have 839 kilojoules. We have 495 kilojoules. We have 799, and then 467. Remember, all kilojoules per mole. And then now calculate. So I want you to try this out, and then I'll write the final answer. So pause now, try to calculate it all. Okay, so it is negative 1,228 kilojoules. So therefore, we have a negative value of enthalpy, and that means that more energy is released when the bonds are formed. So therefore, the energy given to the surroundings is exothermic. Okay. All right, so try out the